Hello everyone. So today I would like to go over the second method we can use for force analysis. So this method is called energy method. So let's recall what we learned previously. So in a mechanical system, we usually define the total energy into uh, two parts. One is kinetic energy, the other one is potential energy. So for the kinetic energy is related to the motion of your objects. So your T is either half mass v square or and half inertial theta dot square, right? So part of the kinetic energy is related to the linear motion. The other part of the energy is related to the rotational motion. So for the U, we usually talk about the gravity or any elasticity in the system. Okay, so the X is the deflection, K is the spring stiffness, and mgh, that's the potential energy change due to gravitational energy. So in this case, let's look at the crank slider in this system. Because we ignore gravity in the system, and then there's no spring is existing in the system, so that's why for this problem your U is just 0. That's very special. So in some cases you might have gravity in your system, so you have to including mgh. So let's look at what the kinetic energy is for this system. So we need to find all the linear and rotational motion. So we have 1, 2, 3 links. So for each link we have a kinetic energy, right? So that means your kinetic energy T equals to T2 plus T3 plus T4. So let's start from the easy case, which is T4. T4 is just a linear motion of a slider, so it's half m4 v4, and then we know the v4 along x direction, right? Because your v4 can only be horizontal, so that's v4x squared. There is no rotation because it's only sliding, so that means the second part is 0. So that's your T4. So let's look at the T2. In this case, your T2 actually is, so when we talk about kinetic energy and when we talk about linear and rotational motion, we're actually talking about the center of gravity, right? So we need to find if there is a rotation around G2 and if there is a linear motion at the point G2. So actually we have both. So we need to first find the linear motion, and then we have to find the rotational motion. Okay, so here you can see that I make a very slight change, and here we only have v4x squared, but here I add an absolute value v2 for v2. That's because when you calculate your linear kinetic energy, that v inside of the expression is actually the amplitude of your velocity. So it's really hard to have your amplitude in your system, but usually we can write these in vector format. You can write it as half m2 v2 transpose dot product v2, and then these v2, they are velocity vectors, and then you can leave the rotational part the same. Okay, so what is v2 vector? So you have v2 vector equals to v2x and a v2y. So it's actually a vector. So let's make a guess. Let's say your v2 vector is somewhere over there, and then it has both x component and y component. When you do dot product, let's say you have a dot product b, by definition, if your a vector is ax, ay, your b vector is bx, by, that means your A dot product B becomes a scalar, which is AX BX plus AY BY. So that's the definition for dot product. Okay. So how can we find V2? And we can easily do these by starting from the displacement or position vector, right? Let's name the position vector of G2 is S2, okay? S2 equals to half of the total length, L2, and then EJ theta 2. And then your V2 vector is just derivative of your S2 vector with respect to time, and then it's actually J theta 2 single dots half L2 EJ theta 2. So the real part is your V2x, and then the imaginary part is your V2y. Okay, so we can do the same thing to find the kinetic energy for T3. So your T3 is half M3 V3 amplitude square plus the rotation part. And then remember, in this time, your kinetic energy is calculated around the center of gravity G3. So again, it has both rotation and linear motion. So that's why you have two terms in the expression. And then again, you can write the amplitude square into the product of two vectors. Okay. 3 dot square. And then using the same method, you can find your V3 vector. And then first of all, you want to find a position vector S3, which is L2 EJ theta 2 plus half of your L3 EJ theta 3. And then we know that V3 vector is V3 vector is L2 J theta 2 dot EJ theta 2 plus half L3 J theta 3 dot EJ theta 3. Right? Okay, up to this point, we know that the total energy of these 4-bar linkage is T2 plus T3 plus T4. We can easily find this energy because it can be written as a function of all the velocities. We have already found all the velocities from velocity analysis. So according to the energy conservation principle, if there is no external force applied to the system, then this energy should always be a constant. But in this case, we actually have external force. So that's why your E is actually not a constant. It's actually changing. Okay, that's your delta E. And then the variation of your E is actually equal to the work W. And then W is work done by external forces or torques. Okay, so what are external forces and torques? We need to go back to the force diagram. So what are the forces we have? So we have the supporting force, that's F1 for Y. We also have the reaction force at the joint, that's F for 3x and F for 3y. You also have these reaction force here, that's F32x, F32y. You have the ground reaction force, F12x, F12y. And you also have a counter clockwise T12 torque generated by the motor fixed to this joint. Okay, so among all these forces, which force are which forces and torque are considered as external force. So for the external force, so we need to find all the forces provided by the ground or by the motor. Okay, so let's look at it here. So we have F12Y, F212X, and the normal supporting force F14Y. So we have F12X, F12Y, F14Y, and the external torque T12. So these are the external forces of the system. Okay, so then we need to find out how much work has been done by all of these forces. So how to calculate the work? So your work is actually force times displacement dot product, or torque times angular position. Okay, so that's the definition of work. So in this case, let's check each force. So F12X, F12Y, so this force is fixed. So this point is fixed to the ground, so it's not moving at all. So that means for these two forces there is no displacement. So that's why they generated zero work. And then for F14Y is always vertical, but then your displacement is always horizontal. So that's why this force doesn't generate any torque, work either. So the only thing left is actually the motor torque. So it's T12 times the motion at that joint. So the motion here is described by theta 2. So that's why you have to multiply it by theta 2. Okay, so that's a work done by the external force. And then we know that this work is going to generate some energy variation. But then it's really hard to find the delta E, because your delta E is integration, and it's from 0 to T, and then that's the changing rate of your energy equals to W, right? So that's your the changing rate of your energy. If you integrate this changing rate over time, that gives you the total energy variation within this time period. It's really hard to have integration in your equation. So that's why we usually do time derivatives on both sides. So you can take the integration out, and then on the right hand side is dw dt, and then the time changing rate of your work is actually the power, right? And then by definition your power is F vector velocity times torque of the angular velocity. Okay, in this case your P is just T12 theta 2 dot. All right, so we know that your P equals to the changing rate of your E. So T12 is something unknown. We want to find how much driving torque we need to generate. And then all the others are known. Theta 2 dot is an input and then your dE, we already know that your E equals to T2 plus T3 plus T4. So that's why your dE dt is dt2 dt plus dt3 dt plus dt4 dt. All right, so let's start from the T4. Your T4 is half M4 V 4x squared, right? So your dt4 dt, let's try to find all the time varying component in this expression. The 1/2 is there, is constant, M4 is a constant. We just need to calculate time derivative for the V4x. So it becomes M4 V4x times A4x. Make sense? So your a4x is the linear acceleration uh, of the block moving along the horizontal direction. You can get these from the acceleration analysis. So let's look at the T2. Your T2 actually have two components. Half m2 v2 vector v2 plus half j2 theta 2 square. So your t2 dt becomes m2 v2 dot a2 plus j2 theta 2 dot theta 2 double dot. All right. So what are these v2 vectors? So your v2 is actually v2x, v2y, and your a2 is your a2x, a2y. So this v2 is the velocity of the center of gravity g2. You have to remember that. And then the acceleration is also acceleration of the point g2. So for the v2, we already give you the expression. Your v2 is already given. It's half L2 j theta 2 square dot ej theta 2. By definition, your a2 is going to be one more time derivative, right? So that becomes L2 to j minus all right, so that's your acceleration. So your a2x is the real part of these a2 vector, and the a2y is the imaginary part. And then eventually, because there is a dot product, so we can write the d2 dt equals to m2 times v2x a2x plus v2y a2y, and then plus j2 theta 2 dot theta 2 double dot. All right, so that's how we calculate dt2 dt. You can apply the same method to find your dt3 dt, right? So you can actually copy and paste. It's just m3 v3x a3x plus v3y a3y plus j3 theta 3 dot theta 3 double dot. And then you can use the same method to find a3x a3y so in the expression. All right, it's just one more time derivative of your v3 vector, and then you find the real part and imaginary part correspondingly. So once you find out the d2 dt, d3 dt, and d4 dt, so that means if you go back to the original equation here, the entire right hand side can be calculated, and then on the left hand side you have t12, which is the only unknown, and theta 2 dot is also known. So that means you only need to solve one equation, and then that equation directly gives you the t12 vector. It's t12 value. So that's the benefits for energy method. You're not gonna solve like over 10 equations. You only need to solve one equation. But then the drawback is you're losing all the intermediate force information. You're not able to get the reaction force at each joint. You can only get the external forces, in this case, which is the torque. Okay? And I'm going to complete these calculation and post it on Blackboard. And then please also check my MATLAB code. The name is lecture 15 underline energy. So in that one, I try to coded up a MATLAB file that helps you to calculate this T12 using energy method.